Questions? Yes. Yeah.
So the reason why it's not considered a field is because it doesn't have an inverse.
That's right. So yeah, Z, the integers is not a field because it lacks, it lacks things like 1/2 or 1/3, things like that. So yeah, and there's a lot of rings, commutative rings that are sorry. There's a lot of things that don't really make the cut as far as a field goes. Fields are very, very special, and I mean there are a lot of them, a lot of examples, but they have the best properties you could want in an arithmetic system. All right. So today, I want to say one more thing about fields. That is the following. So there's a notion of characteristic of a field. So one thing a field has is it has a multiplicative identity. So characteristic field F, I'll just say field, is the smallest integer, positive integer, B, which times that identity equals 0. If it exists. There is no such integer. Do a strange thing. You would think that you would call then the characteristic infinity, but in fact you call it 0. So we call the characteristic 0. So examples. All of the things you're used to dealing with have characteristic 0. So characteristic 0, like char, characteristic is R is 0, characteristic of Q, rationals, same with characteristic of the complex numbers, they're all 0. And then the one thing we learned about that was a field last time is that we could take finite field Z mod P, P is prime. In that case, we would get characteristic of P. There are other finite fields, I want to say, that are prime powers. So you can replace P with P to the n. And there are fields that have that number of elements. But I'm not sure we're going to talk about that anytime soon, if at all. It is not Z mod P to the n. So that's characteristic. There's also a result, which is a result that's useful later on, but indeed in Artin, he doesn't quite have enough tools to prove this, but he asserts it nonetheless. And I'll just mention it, and if we come back to it, I'll explain why, but I don't want to spend too long talking about it. And that's the following, maybe theorem. You don't have to memorize this theorem, but this is, and we encounter it. we take the finite field with P elements and look at its multiplicative group. So remember, this is all the non-zero elements of the field. And the operation is multiplication. This is cyclic. And maybe we can do like one example. Okay, so let's say, for example, a proof, but they look at F7. So what do you think this is going to be then isomorphic to F7 for the multiplicative group? That's another way of talking multiplicative group. Okay, so yes, so F7 without this multiplicative group is Z mod 7. That's just notation, right? But here we're taking the multiplicative group, which means that as a set, this is Z mod 7, but then we get rid of just the 0. A set. And as a group operation multiplication, how many elements are in this thing? 6. And what is this theorem saying? It's a cyclic group. Which means we understand it. There's one generator, and I just take its powers up until I get to the 6th power, and then I come back to the identity, or then I come to the identity. That's actually then means that this is isomorphic to Z mod 6, the additive structure. Let's see if we can find the generator here. I claim 3 should be a good generator. Let's see. What's 3 squared? Mod 7. 2. And I multiply by 3 again, I get 6. Multiply 6 times 3, I get 18. What's that, mod 7? 4. Multiply that by 3 again. Get what, mod 5? And now I just need to multiply 5 by 3. What do I get? 15, which is what, mod 7? So these are, and this is all of them, right? These are all of the non-zero elements mod 7. Well, actually, I was thinking as I was writing this down, what about 2? And I said, oh, wait, 2 cubed is 8. Congruent to 1. That's not going to work. So I said, all right, well, 3 must work. I've been wrong. I take risks in life. I don't know. So there's not, finding generators actually is, takes a little bit of practice. And so, I mean, generally, I don't know. I don't have like a surefire way of just saying this. Well, the same reason you couldn't start with Z mod 6 with 2. If I look at 2, what does 2 generate in the additive group? 2 plus 2 is 4, plus 2 is 6. I get a subgroup of Z mod 6 starting with 2, right? That is only an order 3 subgroup. So if you have a cyclic group, it doesn't mean every single element of that cyclic group is a generator, right? There are only special ones. Now, if you're in Z mod P for P prime, every element is a generator. You're talking about the additive group. The multiplicative group is not. This is, as I said, this is Z mod 6. 6 is not prime. So you have to, I guess the answer is you have to be a little careful of choosing what elements are generators. Some things will just generate subgroups. But this is kind of surprising. I mean, this is kind of surprising that that it's a cyclic group in a sense. And it really does rely on the field structure. It's not just something that you should expect. And it, as Artin says, it uses, I think, a classification theorem that you get later on. So the proof is not something we can really do right now. That's not hard to understand. It's just kind of a little technology. Okay, next section, 3.3. Main players, vector spaces. What is a vector space? Okay. Definition. So a vector space V over a field F. Now we're really kind of moving out from case of just the real numbers or the complex numbers. Over field F. Set the two operations. One is addition. Addition. Scalar multiplication. These operations have different inputs, as we all know, right? Addition, we take two vectors and we'll return a vector. Scalar multiplication, we'll take an element of your field and a vector, return a vector. This is very familiar to you all from Calc 3, whatever, right? You can add vectors, and you can scale and multiply them. Same idea. But this is sort of the abstract version. Of course, here we're saying when I say this is we have a vector u and v. I want to add them, I just write u plus v. I have a scalar lambda, and I have a vector v, and I want to scale multiply, I just write lambda v. These have to satisfy properties. What are the properties? Well, addition should form an abelian group. So be with this addition forms an abelian group. And the second part is that you have a distributive property. Well, there's actually associativity and distributive property. Also, maybe I'll write associativity, scalar multiplication. Which is a little funky, but okay. What does it mean? It means just what you think it means. If I multiply two scalars and then multiply a vector by that product, it's the same as first multiplying by one of the scalars and then multiplying by the other. And then distributive property. I multiply a sum, oops, I guess I just need one lambda here. I multiply a sum of vectors by lambda, I can distribute to each of the individual sums. That's it. That's the definition. Now, I guess we also have a distributed. I'm not sure if it's necessary, but okay, let me include it. There's also this distributive property if I add two scalars. It's a sort of left and right distribution. So what are the examples? What are the examples? The most common and familiar example that you know of a vector space is just taking column vectors. So column vectors. And this is a main example, which we'll see why in a moment. So we can just write F and the column of entries in your field. Scale multiply each entry by your scale. You can add them. So just what you expect. Of course, there's natural examples of vector spaces, like continuous functions on R. It's denoted CR. You can add two continuous functions. You do it all the time in calculus, right? You can scale multiply them by real numbers. This is over reals. Field is the reals. You can also make this instead into differentiable functions, or twice differentiable functions, or smooth functions, which are infinitely differentiable functions. There's all kinds of notations. These are all vector spaces. These vector spaces are the obsession of fourth department here. Maybe fourth to a sixth of all mathematicians. The eighth. Analysts spend all their time thinking about these spaces or variants. They want to solve differential equations. These are infinite dimensional vector spaces, and you can start defining linear transformations and all kinds of things using differential equations and start thinking about them in the context of vector spaces. And there's all sorts of theory associated with these spaces. Those in physics, no. I'm sure you've seen Hilbert spaces, things of that sort, or you will if you haven't. This and its differentiable versions is a very important example of vector spaces. Okay. Of course, there's many variants. You can also talk about polynomials, say, up to a certain degree. Say, maybe you can talk about all polynomials, but we can say polynomials up to degree n. So these are guys that look like this. Constant term A naught, linear term A1, up to a degree n term. This is nx again. You can add these to get a polynomial of the most degree n. You can multiply them by an element of your field. These can all be in. This is what you would write. This is polynomials, coefficients in your field. Coefficients F. A very important thing to consider. These are some examples of vector spaces. Very, very common examples of vector spaces. Now, you may, as is totally natural and healthy, I want to say, you may be rejecting mentally everything I'm talking about. It's like this is just needless abstraction, right? Okay. Why do we consider vector spaces? Why not just this example? Why not R to the n even? Why even deal with fields? R to the n, describes n-dimensional space. What do we need with this V and all this weird, abstract properties? Why? So there's actually, I want to say, an extremely important reason why we want to abstract to this general vector space. And it's that the reason is, the way I can explain this right now, is that we don't go around in our world, right? Like let's say I asked my daughter, where'd you put the bowl of cereal? She doesn't go and say, it's at 275. Just say that to me. She says it's over there. Right? That's what she said. She says it's over there. There's a place, like a geometric space, right, that we're in. And it doesn't come with a grid. It doesn't come with this sort of like, coordinate system that we all agree we're going to call all these points this point. It doesn't happen. So there is a space, the vector space we live in, the three-dimensional vector space we live in. Its points don't have numbers. We do violence to that space. We do obscene things to that space when we call it R3. We impose a grid. The choice. We're doing that. When we make that choice, we have to be aware of it because someone else, daughter maybe, makes a different choice, a completely different choice. And so we don't understand sort of the abstract properties of it. We're not going to understand how to go from one choice to another, how they're related, and how we can, program computers to relate them or satellites or whatever. So the thing I'm trying to emphasize is that this is a good prototype. Once you have a grid, you can do a lot of great things in compute, but there is a choice in it. And we need to kind of keep that in mind and try to study the intrinsic things about it and separate those from the choices. Is it kind of sensible, what I'm saying? If you're in physics, again, this is like a gauge choice of gauge, fixing a gauge. And a lot of theoretical physics is all about trying to achieve gauge independence. I'm sure there are other, I got an undergraduate physics degree and a lot of my math kind of overlaps with physics. So I kind of rely on, I know certain things about physics where I can, but there are all kinds of applications have this in it as well. So I'm sorry if I'm being biased and you don't care about physics. It's okay. All right. So that's enough of me waxing and waning about stuff. Get back to some definitions. So we need a way, just like for groups, we need a way of relating two different vector spaces. Right? We had this notion of homomorphism for groups that related to groups. That okay, there's some kind of way from going from one to another. And for vector spaces, we have also a similar kind of way of relating them through a map. It's called a natural transformation or linear transformation. So a linear transformation didn't see this in art and right yet, but I think it's important to know it right now. A T from B to B prime, these are vector spaces. Spaces over field F. Is a function satisfying two rules, two identities. Meaning that if I take two vectors and I add them together, this looks a lot like a homomorphism. Indeed, it is a homomorphism of the additive group. So T of the sum of vectors is the sum of the values of T. But also we can do the same thing with scalar multiplication. in a way, because what we asked with scalar multiplication is t doesn't do anything to the scales. That's what we ask. We say that t, the scalar can come out of t. T is a map from B to B prime. T doesn't map F to any. F is just F. It's a linear transformation. Now we say it's an isomorphism. If it's bijective, or equivalently if it has an inverse. This is the extent of the definitions. Let me give an example for 3.3. Let me give an example of an isomorphism. That wouldn't be hard to show. So, example. This is very, I think you all will feel totally comfortable with this. R2, find T from R2 to C as vector spaces over. So you really need to, everything is dependent on the field you're working over. When I say over, I mean each of these are regarded as vector spaces with the field R. What does it do? It takes column vector AB. It's A plus BR. That's it. So you can certainly, I mean, I'll let you verify that certainly this is a linear transformation. And this is certainly bijective, right? I mean, you can kind of see A and B are identified with the real and the imaginary. Yes.
So does the fact that it's vector spaces over R mean we couldn't scalar multiply by a complex number? Is that?
Well, that's the question. So if, well, you can't, yeah, I mean, so C is naturally a vector space over C, because I can multiply. But in order to define R2 as a vector space over C, I would need to give you some notion of what it means to multiply by I. You know, a column vector. Now you can do that, but it's not something we've done, so I didn't want to. That actually, there's this notion of like an almost complex structure, but that's maybe all kinds of notions. Yeah, I think this is as being over R. Questions? All right, so this is basically, so this is a lot of the sort of fundamentals, basic notions of vector spaces. Vector spaces are the thing that we generally work with the most. They have very, very tight structure. We can understand a lot about them. They're much simpler than groups. And yeah, so we're going to get into it just for the rest of today and on Friday and just learn some real basic things about them, in particular, a little bit about the dimension theory. So for that, I want to move on to 3.4, and we'll talk about dimensions of vector spaces. Okay. So there's a set of definitions, which if you've taken linear algebra, you'll see in many of them before, not all of them, hopefully all of them. And if you haven't, then we'll learn them now. But they're not too bad. So we're going to fix, for now, a V, a vector space over a field. Okay. Need some definitions. given vectors, so we have a set of vectors, V1, V sub n. We call any kind of expression like this, A1, B1. I can scale or multiply each of the vectors by a different scale, a priori different scale, doesn't have to be different. But if we scale multiply each vector by some scale in F and add everything up together, we call this expression a linear combination of the V dots. It's a linear combination. Use that language very frequently. Vocabulary. Here are the AIs. These are in our field. Those are the only things we're allowed to model. Okay. Now, if we have a linear combination of some vectors, say V1 through Vn, and it equals 0, call that a linear relation. So if A1, B1, yeah, 0, call this relation. There's a can anyone give me a linear relation? Let's say I give you n vectors, V1 through Vn. I say, tell you there is a linear relation. Can you tell me an example of one? Yeah, all of the A's are 0, right? Yeah. That's called the trivial linear relation. And it's okay, but it's an important one. So if all A's equals 0, then say this is true. Now, that's kind of silly. So, however, there are certainly examples of vectors where that's the only one. That's the only linear relation amongst the vectors. If that's the case, all those vectors linearly independent. If this collection V1, say through Vn, has no non-trivial relations, say so all of this linear independence, the thing to keep in your mind is what you're saying, if it's linearly independent, is you're saying that this kind of relation here only implies that the coefficients A1 through AN, that they're all 0. You have such a thing simultaneously. Okay. There's another thing we can do with linear combinations. Rather than setting them equal to 0, we can just take the set of all of them. So we have a name for that. We call it the span. So given a set of vectors, here it doesn't have to be finite. It could be whatever you want. I mean, I guess, to be honest, I really didn't need this finiteness. Should have just, okay, I'm going to keep it as I wrote it, but you can imagine this as an infinite set. So you can take any infinite set and talk about linearly independent so that no subcollection has, no finite subcollection has a relation. Not a relation. So I'm just going to leave that as. All right. So given a set S of vectors inside of our vector space B, it's just a subset, B infinite. we call set linear combinations vectors in S span of S. Okay. Now, these are the two, I want to say that these are the two kind of key things that would be great to have simultaneous. Except it spans, say, all of V, and that is linearly dependent. So it's a great thing to have. It's equivalent to doing what I was saying earlier, which is sort of imposing a grid, in a sense, on your vector space. So what we want to do, take a definition of such a thing. That's easy enough. A basis. We say B is a basis. Some people want B to be ordered, like not just a set, but an ordered set. There's a reason for that, but I'm going to just leave it as a subset for now. Okay, so let's say B is just a subset. It's a basis if it's linearly independent. And the span of it is everything. We call B finite dimensional. It has a finite basis. Thus finally getting to the dimension. We haven't really put a number on it yet, but that's, all right, that's a lot of, I got 5 definitions at least on the board here, on the, whatever this is called, screen. And they're very important. Yes, please, Matt.
The span.
Yes.
On the set of linear combinations. So the set of little s, the little a are linear combinations. Correct?
I'm sorry, I couldn't hear you. I didn't just hear.
Defining on the span.
Yes.
So I can see how we would have a set of little a. Right. Where does the V set come
So the A's are just coefficients. They're just elements of your field. So the S is just any collection of vectors. So you can take your pick, whatever you want. Take 5 or 6 vectors, take a million, take an infinite set. You've got a set of vectors, and then you choose whatever A's you want, whatever coefficients from your field you want, any and all of them. And you form these types of sums. Like scale, multiply, and sum things up, however you want. Take all possible ways that you can do that, only using the vectors from S. This will give you something that we call the span S. In fact, this thing that you get is a vector subspace. Namely, it's closed under addition and scalar multiplication, clearly, because you can always take 2 linear combinations and add them to get another linear combination. And that's it. So it does form a subspace of B. Yes.
So like when you said earlier that the polynomials up to degree n were a vector space, is that an n-dimensional vector space then?
Nope. Close. Off by 1. Got constants. Okay.
some scalar multiples of those vectors.
Linear combination is exact. Linear combination is a sum of scalar multiples. Let's do an example. Let's get our hands dirty here. Example. There's some in the book too. Let's start with our favorite, most familiar column vectors. But let's do it in F3. Just to prove that we're sophisticated people. Let's prove. Right. This is my set. Okay, Matt? This will be my set of vectors, v1, v2. So let's call this a subset. Of course, not all of them. It's a subset. But now I want to talk about the span of S. What do people think? What's V1? What happens if I add V1 and V2? That's a linear combination. What is it? So I'm after this. What's V1 plus V2? 0, 2. What's 2 times V1 plus V2? 1. Right? 2 times 2 is 4. Mod 3 is 1. Good. Now, once you see these two guys, these two fellas lurking, what do you think you're going to get if you take linear combinations of these? Anything you want. A times this plus B times this is just A, B. A and B are any elements of your field of F3. So once I can identify, these are called the standard basis vectors. Once I identify that they're in this span, then I can use anything in the span, take linear combinations of it, and get anything else and get other things in the span. So I'm saying that I can get everything from these three vectors just by taking linear combinations. So we're after it, and we found it. Span is everything. Question? Okay, so I got the span, and I say, oh, it's a basis. But wait a minute, I have another condition. Basis also needs to be linearly independent. Let's check. Let's look for, let me write linear combinations in a funky way. Let's say I want A1 plus V, oops, sorry. A1, V1 plus A2, V2 plus A3, V3. This is going to be something. Star, star. I know what it is, what the stars are. But I can say the following thing, that if this is what it equals, then I claim that this is also, let me just make my V1 a column vector, or a column, not a column vector, it is a column vector. We make it a column of a matrix, V2 another column, and V3 a third column. We do matrix multiplication by A1, A2, A3. I claim these are going to be equal. And if you don't believe me, just see that this is what you do when you do matrix multiplication is you multiply this by this, multiply this by this, and you multiply that by that, and you add everything up. So that's precisely this linear combination. So now the question is, I want to show that they're linearly independent. So I want to show that. To show that means that this will never equal 0 unless A1, A2, A3 are all simultaneously 0. Linearly independent means this equation has no non-trivial solutions, which is zero vector. You tell me, does that sound right to you? Is this, I mean, by which I mean, is there only a trivial? No, it's not. This is a 2x3 matrix. Right? 2x3 matrices, if we put them in reduced row echelon form, we'll always have a free variable. We'll always have a column that doesn't have a pivot in it, which means there's going to be some kind of free variable. There's going to be a lot of solutions to this equation. At least one dimension, one extra free dimension of solutions. So there is indeed a non-trivial linear relation, which means they're not linearly independent. Indeed, I guess we could, if we want, we could just say, take, I guess, 2, 1. This will give us, just see that we have a non-trivial. Multiply B1 by 2, B2 by 1, B3 by 2, add, so you get 0. This is not linearly dependent. However, if I take any two of these three vectors, any two, I will get linearly independent sets. So you will get, there are subsets of these guys that are based. Now, to your point, that's example 1. Example 2, what about, say, polynomials of degree less than n, less than or equal to n? Well, you can consider the following set. 1x, x squared, up to x to the n. These are the monomials. Poly meaning many. Many monomials, add them up. Polynomial. So these guys actually do form a basis. Indeed, if I take a linear combination of these, we can write down what they look like. We take A naught times 1 is A naught. And they look like this. This is exactly what a polynomial looks like. We get any polynomial by taking a linear combination of degree less than or equal to n. And furthermore, the only way this is going to be the zero polynomial is if all of the coefficients are zero. If anything is non-zero, it's definitely not a zero polynomial. Take some sort of derivative of it and get 1. All right. Good. So what we want to do, the next step, which we'll get to tomorrow and finish up, is I want to show, which is not a very hard thing to show, but we'll do it, that if we have a finite dimensional vector space, the number of elements in any given basis, any two given bases, will be the same. If I have one basis with 5 elements, I'm not going to have another basis with 6 or 8 elements. Once we know that, we can talk about the dimension of that vector space as being the number of elements in a basis. That gives us a legitimate notion of what the dimension of a vector space is. From there, we want to do 3.5. 3.5 is all about imposing that grid. What happens if we choose different bases how do we make the transformation from one kind of grid to another? To a choice of coordinates. Bye, guys. Thanks. See you on Friday.